Hello everyone, welcome back. In this video, I will be covering section 2.8, the derivative as a function. In the last video, we saw that the definition of the derivative is nothing but the second definition of the slope or the tangent line. So we interpreted right from the beginning of this chapter 2, we saw how the slope of the secant lines, the limit value of that becomes the slope of the tangent line. Same way, how the limit of the average velocities become the instantaneous velocity. Then we know now from the previous section, the word derivative, also the rate of change, means change in position over change in time or change in y over change in x is nothing but the derivative, whose definition resembles the slope of the tangent line, right? So with the limit as x approaching 0. So we are now going to consider the derivative itself as a function. So for each and every point on a curve, so suppose we consider a curve, let's say a parabola. At this point, the slope is different from at this point. So the slope actually varies from point to point. The slope here is different from the previous. So at every point on a curve, the slope changes. So we are going to consider the slope itself as a function because it varies from point to point. So the derivative of a function f at a fixed number a is f prime a, which is limit of f of a plus h minus f of a over h, limit as h approaching 0, provided that this limit exists. If we replace a in the definition by definition 1 by the variable x, we obtain the derivative of f as limit of f of x plus h minus f of x over h, and limit as h approaching 0. So all we do is replace a fixed number by a variable x, the definition. So now this f prime x becomes a function because the slope itself becomes a function because of its varying nature from point to point. The graph of a function f is given in figure. Use it to sketch the graph of the derivative function f prime. So given a graph like that. So which if you notice that it decreases and then increases and then it falls again, it increases. Right? So what we are going to do, so all these points here are connecting x comma y. So in this graph, the points are x coordinate and the corresponding y coordinate. Now we are going to create a new graph connecting x and then its slope at x. So instead of y coordinate, it's going to be the y coordinate of any point in the new graph is going to be the derivative at that point or the slope at that point. So let's give some examples. Let's take some points on the graph. Let's say I take negative 0.5, for instance, negative 0.5. So what is the slope over there? The slope over there is kind of negative, right? So it is negative 0.5. The slope is some negative number. Right now we know that it is negative because if you draw a line, it is going to be tangent line there. It's going to be a decreasing one. The function is decreasing there. The slope of the tangent line is going to be negative. And what happens at 0? Still, the slope at that point is negative. But if you compare to the previous point versus this point, the previous one has more slope than the tangent at 0. What is the tangent at 0? At 0 is somewhat like that. So the previous red line is more, has more slope than the green one. And now you're going to consider this particular point, this particular line here, where the tangent is horizontal. So the slope is 0, which happens at, say, at 0.5 approximately. So at 0.5, the slope is 0. Then the slope actually increases, right? Increases between 0.5 and slightly more than 1 even. So it is increasing. So at 1.2, if I consider, at 1.2, I get a positive slope. So somewhere here, I get a positive slope. Then at the point, say 1.5 though, I get a horizontal tangent. So m equal to 0. So it was 0, and then it became positive, then it reduced, and then became 0 once again. Then beyond 1.5. So for example, if I take between 1.5 and 2, let's say, then all the slopes are negative. Okay, consider this point to be 2. So all these slopes here are negative between 1.5 and 2. Then after that also, after 2 also, if you notice, the slope is going to be negative between 2 and 3. Between 2 and 3, the slope is negative. So at 2.3 roughly, the slope becomes 0. At 2.3, the slope becomes 0. Then after 2.3, the slope becomes positive. Okay, any number after 2.3. 2.3 and up, the slope is positive. Okay, all these slopes are positive. To be more specific, if you really want to know what the slope is at any point, what you can do, draw a tangent line and go vertical over the horizontal. So you can find out this is like change in y, change in x. If you find out the ratio, that will become the slope. Difference in y over the corresponding difference in the x. So what does this table tell us? What does this table tell us? So if you look at, if you join the point x with its derivative, so it starts off more negative at the point negative 0.5, then at 0.5, so it goes more negative and then less negative. It becomes 0 there, right? At 0.5, the slope is 0. So it crosses the x-axis. And then it goes positive, so it goes up little. And then what happens at 1.5? 1.5, it becomes 0. So at 1.5, it becomes 0. Till then it is positive. Then after that 1.5, it becomes slightly negative. Then at 2.3, it becomes 0. So it crosses the x-axis. It becomes 0. So remember that I'm connecting x with f prime x for the darker graph. Then 2.3 and up, it becomes positive. So the derivative graph, this is known as a derivative graph. The derivative graph looks like this. So given a graph, how do you find out the derivative graph? You draw tangents at different points and determine the slope, and you create a table between the point and the slope, and then the y-coordinate of every point will be the slope at that point. You create a new graph that way. The next example would be, If f of x equal to square root of x, find the derivative of f, state the domain of f prime. So we are going to use the definition of the derivative. So we know that derivative is limit as, you can use either the definition we have here, f prime x is f of x plus h minus f of x by h. So we can use that, h approaching 0, f of x plus h minus f of x divided by h. You can use this definition. So f of x in our problem is square root of x. So f of x plus h is obtained by changing x to x plus h. So the input x changes to x plus h. So we get limit as h approaching 0, x plus h minus square root of x, that's for f of x, divided by h. As a numerator involves difference of two radical, we'll use the usual technique of multiplying and dividing by its conjugate, which is connected by plus, divided by square root of x plus h plus square root of x. So now we combine them. If we have to multiply the numerator, you see the same term on the numerator, like one with the positive sign, one with the negative sign. One is connected by a minus, the other one is connected with plus. So it is difference of squares on the numerator. So continue writing that limit as h approaching 0 till you substitute h equal to 0 at the last step. So it is square root of x plus h the whole square minus square root of x the whole square, difference of squares, divided by h times square root of x plus h plus square root of x. So this implies limit as h approaching 0. Square and square root, they cancel out, giving you x plus h minus x divided by h times square root of x plus h plus square root of x. These two cancel out. So you get limit as h approaching 0, h divided by h times square root of x plus h plus square root of x. At this point, you can cross this out. Numerator will be 1. And also you make sure to substitute h equal to 0. So it will be 1 divided by square root of x plus 0 plus square root of x. In other words, it's 1 over 2 square root of x. So f prime x for f of x equal to root of x is 1 over square root of x. So you will see many of these problems that we have done in this chapter, in the next chapter, where after we learn the rules for the derivative, the laws of the derivative, we'll understand that these problems become very easy. We don't have to use definition 1 or 2. This problem is also asking for the derivative of f, domain of the function and its derivative. So domain of f. So f is root of x. F prime is 1 over 2 root of x. Right? For the domain, it's going to be, what is the domain of a radical function? The radical function looks like this. We have to start only from 0 and go upwards. So the domain is all from 0 through infinity, including 0. But on the right-hand side, for the f prime x, the domain is root of x lies below. So you cannot substitute 0 for the denominator, but still the domain will be 0 through infinity, but 0 is open. So 0 is not part of the domain for the f prime function. If you use the traditional notation y equal to f of x to indicate the independent variable, x, and the variable y, then some common alternative notations for the derivative are as follows. All these notations were possible by the mathematician Leibniz. So we are able to now use calculus in a precise way because of the symbols are also helping us to write calculus in a precise way. F prime x is y prime, and it can also be written as dy by dx, derivative of y with respect to x, or df by dx, because y is after all f. Or you can also write d by dx of f of x. Or you can use an operator uppercase d of f of x, or uppercase d f of x with respect to x. The suffix x stands for derivative with respect to the variable x. The symbols d and d by dx are called the differential operator. Called differential operators because they indicate the operation of differentiation, which is the process of calculating a derivative. Next definition, a function is differentiable at a at the point a if f prime a exists there. It is differentiable on an open interval ab, or open a infinity, or open negative a infinity a, or negative infinity infinity, if it is differentiable at every number of that interval. Where is the function f of x equal to absolute x differentiable? So we know how to graph. We'll start off with the graph of absolute function. So the graph of absolute function looks like a V-shaped graph, right? So it is here, it is absolute x equal to x because x is positive. And here, absolute x will be equal to negative x less than 0. Right? So now if you find out the derivative of this, f prime x, for the right-hand side, the slope is equal to 1. So for x more than 0, f prime x equal to negative 1 for x less than 0. So notice that above 0 and below 0, the derivative exists, and it's equal to 1 and negative 1. So what happens at x equal to 0? Does a derivative exist there? Does a derivative exist at that point 0? So we will evaluate f prime 0 and see whether it exists or not. We will evaluate what is happening at, what is the value of f prime 0. We are only going to prove that f prime 0 does not exist by calculus methods. So find f prime 0, which is by definition a limit. Either I can use definition 1 or definition 2. You can also use definition 2. Let me use definition 1 for a chain. Limit as x approaching 0, f of x minus f of 0, over x minus 0. So it is limit as x approaches 0, f of x. What is f of x? Absolute x. What is f of 0? F of x is the given function, absolute x. What is f of 0? Absolute 0, which is 0. So 0 divided by x. So ultimately this definition becomes limit as x approaching 0, absolute x over x. So let's divide this into left limit and the right limit. So this will be equal to, if I consider the right limit, let's say, we'll call it step 1, right? So now we are considering the right limit for limit as x approaching 0 from the right side. Absolute x over x. From the right side of 0, that means x is more than 0. So limit as x approaching 0 from the right, then absolute x will be equal to x. What is the definition of absolute x? Absolute x is x whenever x is more than or equal to 0. It is equal to negative x if x is less than 0. This is how we define the absolute function. As we are approaching 0 from the right side and x is more than 0, the numerator absolute x will be simply x from this definition. So the denominator is x, so it is equal to 1. On the other hand, the left-hand side limit, which is limit as x approaching 0 from the left, which is also equivalent to saying x is smaller than 0, absolute x over x is limit as x approaching 0 from the left. Now, absolute x will take up negative x for x less than 0, correct? So it is negative x over x, which will be negative 1. And earlier, we have actually seen the graph of absolute x over x. It will be this line for absolute x over x for x more than 0, which will be equal to 1, y equal to 1. And absolute x over x will be equal to negative 1 whenever x is smaller than 0. All right. So the right limit and the left limit are not equal. So in one, f prime 0, which is limit as x approaching 0 of absolute x over x, does not exist. Next theorem, if f is differentiable at A, then it is continuous at A. So whenever we have to prove that f is continuous at A if limit x approaching A of f of x equal to f of A, right? This we saw in 2.5 as a definition, right? This is the definition of continuity. In other words, we have to say that f of x approaches f of A as x approaching A, or the difference between the two is 0. That's what we have to show. We have to show f of x approaches f of A when x approaches A in order to prove that it is continuous. So let's consider the difference f of x minus f of A, which I can write f of x minus f of A over x minus A times x minus a. I'm multiplying, dividing by x minus a. Let's say I take the limit, absolute, and also I take the limit. I take the limit as well. Here also you have limit. So this part, f of x minus a, f of a over x minus a, limit as x approaching a, is nothing but f prime a, because it does say f is differentiable at a. So f prime a exists. That is the first part. And the second part is limit as x approaching a of x minus a. X minus a is a polynomial. So you notice that it is f prime a times. Now you plug in x equal to a. So what happens here? It becomes a minus a, which is 0. 0 times f prime a is 0. So what have we proved here? We have proved that limit x approaching a of absolute f of x minus f of a equal to 0. This means limit of f of x is nothing but f of a as x approaching a. This shows that f is continuous. Continuous at x equal to a. So differentiability implies continuity. How can a function fail to be differentiable? So whenever there is a corner or a cusp, you cannot draw a tangent at. So at A, if there is a cusp like this, then there is no, or a corner, it's different, not differentiable at the corner. Whenever there is a discontinuity, like you have discontinuity at A, so there is no, the graph will not be differentiable at that point A, wherever the discontinuity occurs, or wherever the vertical tangent is. What is the slope of a vertical tangent? Slope of a vertical line is undefined. So slope of a vertical tangent will be undefined. So wherever the graph has a vertical tangent, there the function, the graph will not be differentiable. If f is differentiable function, then its derivative f prime is also a function. We saw that the derivative can be considered as a function. So f prime may have derivative of its own denoted by f prime prime, which is f double prime, the second derivative. This new function f double prime is called the second derivative of f because it's derivative of the derivative function. Using Leibniz notation, we find d by dx of dy by dx, which means derivative of the first derivative is the second derivative, which we write as d square y over dx square. If you take the derivative of the second derivative, that will become the third derivative. That will become the third derivative, which we rarely use, which is called jerk in physical application problems. So f triple prime x can be interpreted as a slope of f double prime x. So y triple prime is same as f triple prime x, which is derivative of the second derivative, which we can write as d cube y over dx cube. So like this, we can actually continue taking the derivative of each function, higher order derivatives, but it's not feasible to write the 10th derivative as 1, 2, 3, 4, like the slashes like that. So instead, we write that as f with the superscript 10 in parentheses. That means it is the 10th derivative. So y superscript n here, consider the nth derivative. Problems given from the exercise. So there are some of them like practice test 28 will be shown in a video, separate video. Then you can check it out. So now you are given a graph, set of graphs in blue. Match the graph of each function a to d with the graph of its derivative in 1 through 4. Give reasons for your choices. So we have to choose the correct derivative. And also we have to give a reason why we picked that graph. Okay. So if you look at the first one, so the slope, if you look at the slope, we are looking at the derivative function, which is on the right-hand side. So you start off negatively because on this side, the slope is decreasing. So you notice that it starts off negatively and then it goes to 0. Then it starts and then it goes positively. Then it goes to 0 at this point. Okay. At this point. So if I call this point is say 1 and this point is say -1. So you will have so at -1, the graph will cross. At +1, the graph will cross in the derivative one. So which looks more like number 2, because I see at -1 and +1, the graph crosses. So if you look at the slope of this particular one, so -1, there is a horizontal slope. So there is a point and f prime x. And then there is a point and the derivative at that point is 0. So you have to look for the graph with the -1 y coordinate 0, +1 y coordinate 0. So the answer to this one looks more like figure 2. Then what about the next one? So here you notice that at -1 there is a corner, at +1 there is a corner, there is no tangent. You cannot draw a tangent. So there will be a discontinuity at those points at -1 and +1. So it looks more like, because at -1 there is a discontinuity, at +1 there is a jump discontinuity as well. So for B, this is more like, the answer is more like 4. It matches with 4. Let's look at C. So you have a decreasing slope, and then at 0, there is a horizontal line, a horizontal slope, and then it increases. So it's more like number 1, because it starts off negatively, and then at 0, it crosses 0, and then it starts off positively, and then it goes horizontal. It becomes horizontal towards the end, so the slopes become 0. The last one, D, so you have an increasing slope, so positive, and then at say -0.5, you have a horizontal slope. And then at 0 also you have a horizontal slope. Then at 0.5 you have a horizontal slope because m equal to 0 there. So which definitely looks like number 3. Number 3. You notice that at this point, 0.5, it crosses the x-axis. The slope is 0 there at 0.5. At 0, the slope is 0. And then at 0.5, the slope is again 0. So the slope, you have a horizontal. So at 0.5, it crosses the x-axis. So it is more like 3. So given a graph, see how the slopes are changing at every point. Then you connect the point with its slope to make the new graph. So we are connecting any point with its slope. So notice here negative at a negative 0.5, there is a horizontal slope. So if you notice here in this graph 3, so negative 0.5, it crosses the x-axis. 0.5, again, it crosses the x-axis. And here it is increasing function. So the slope is positive. So what we see here is a positive slope, right? So it starts off positive. So here you have a positive slope. That's why in this graph, the y value is positive. And then it decreases towards the end in this graph. That means the slope is negative. That means on the right side, you see in 3, it is falling. It is going below the x-axis. So make a careful sketch of the graph of f below and sketch f prime. Can you guess a formula for f prime from its graph? So this being a popular function, let's see what the derivative graph looks like for f of x. F of x equal to sine x. Number 16, f of x equal to sine x. So we know that for f of x, if I write x and y, so I'll notice that sine 0, 0, it is sine 0, which is equal to 0. Then at pi by 2, it becomes 1. Then at pi, it becomes 0. At 3 pi by 2, it becomes negative 1. At 2 pi, it is equal to 0. So if I graph the sine x graph, 0, pi by 2, pi, then 3 pi by 2, then 2 pi. So it goes up. It starts off 0, goes up at pi by 2 to 1, then it declines to 0, then it goes to negative pi by 2, negative 1. It completes one cycle. This is sine x, right? Now we are going to find out the derivative. So what we are going to do is to create another table and connect every point with its derivative, which means slope of the tangent line at that point. So let me start up with 0. 0, the slope seemed to be there. It seems to be like a line passing through the origin, which looks like y equal to x. So what is the slope of this line? 1, correct? So the slope there is 1. Then what is happening at pi by 2? At pi by 2, the slope is horizontal. There you have a horizontal line for the tangent. So the slope is 0. Then at pi, you notice that it is exactly opposite to the tangent at the origin. So if the slope was previously 1, the slope would be negative 1. So at 3 pi by 2, you have a horizontal tangent. So at 3 pi by 2, the slope is 0. At 2 pi, it exactly looks like the first tangent line at 0. The slopes are the same. They are parallel to each other. This one and this one, they are parallel to each other. Therefore, they have the same slope. So if I draw a new graph with these points in mind, 0, 1, and then at pi by 2, it crosses 0. At pi, then 3 pi by 2, and 2 pi. Then at pi by 2, it becomes 0. Then at pi, it becomes negative 1. at 3 pi by 2, it is 0. At 2 pi, it is equal to 1 again. So this is nothing but the derivative graph of the original graph sin x. It so happens that the derivative graph is a cosine function. So the question is also asking find out a formula. So if f of x equal to sin x, then its derivative would be cosine x. This is something interesting that we proved by way of graph and using the point with the derivative with the slope, connecting every point with the slope and creating a new graph. So this completes chapter 2. See you guys for chapter 3. So let's take a look at these videos, and if you have any questions, you are most welcome during my office hours for any help.